Good luck with the clicker. Okay, thanks for having me. Apologies if I fall asleep. I've just got off a plane from San Francisco. The beer is not helping. So I thought it'd be a good idea to have a beer, relax me, but no, I am close to falling asleep. But anyway, so I'm going to be talking about AVX-512 assembly, I should say assembly language and FFmpeg. Do I have a pointer just to check before I start? Yes, okay, good. Right, so this presentation was written for a slightly different conference, so I thought I would start right at the basics. What is assembly language, for those who aren't aware? Assembly language is a low level, as in very close to what the hardware is doing, programming language. And I'm going to be talking mainly about Intel assembly language. There are other types, ARM, Motorola, etc., etc. And this is kind of on the right an example of said assembly language. So you have what's very famous about Intel assembly language is it is broadly backwards compatible to the original Intel CPU from 1972. So you have various instructions here and various registers that the processor operates on. And by pure coincidence, I happened to go to a talk last week in Silicon Valley from a gentleman who actually used sulfuric acid to actually melt down the die of the 8088 CPU. And he actually explained why some of this is the way it is. Because you would notice that this is the registers are not in alphabetical order, and that dates back literally from 1972, where AX was, I think, the accumulator, C was the counter, D was data, and B was the base. And then these things have been added much later on. And broadly speaking, you could still write code today that works on this CPU from 1972. And I think in some industries, I think railways in the US in particular, I think there's some very specialist industries where this really does matter in terms of certification for legal reasons. Maybe not from the original 1972, but certainly from processors from, say, the 80s. So languages that we're kind of used to, like C, these are compiled into assembly language. And you have these things called mnemonics. So like move, this is add, pop, multiply. So these are just human readable versions of just bits of hexadecimal values that the processor actually understands. And these sort of instructions operate either on memory of the device or on these general purpose registers. So what is AVX-512? AVX stands for Advanced Vector Extensions. This is what's known as a SIMD, single instruction multiple data. So the ones before, clicker's not working, yeah, are not SIMD, so it's a single instruction and a single piece of data, so it multiplies a single piece of data. Let's go back, go forward. SIMD is when you have a single instruction and multiple bits of data are multiplied. I'm sorry to the gentleman sitting there because you might get laser eye surgery without asking for it. So, yeah. So this is a new instruction set since 2017, and more recently AMD CPUs. These have much larger register sizes. So the ones I showed before were 32-bit, whereas these are known as 512-bit ZMM registers. Lots and lots of new instructions that do all sorts of interesting things. Talk about those in a minute. Op masks, which let you sort of, I'll explain, but sort of make decisions based on an individual element in the register. Comparisons, this was the thing that was missing. All sorts of other things not so interesting in multimedia, cryptography, neural networks. So this presentation has a lot of jargon, but the key thing to understand is that in FFmpeg, high schoolers have gone and written assembly language. Once you get past the jargon, it's actually very intuitive, in part because you're actually working very close to the metal of the hardware. So there isn't a lot of complexity once you really understand the jargon. So why is this relevant now? I've obviously said AVX-512 has been around since 2017. Well, all the systems, and the first sort of systems were known as Skylake systems, had quite large performance throttling when using larger registers. So you use these ZMM registers and you'd see suddenly the CPU throttles down by 30%. This was a big problem, and it was key reason AVX-512 remained unused in things like multimedia, because in multimedia you have a mixture of non-SIMD instructions, so just normal C code, for example, and AVX-512. Whereas, for example, in academia, in sort of fluid dynamics, you may just have entirely AVX-512. So let's say AVX-512 makes your academic application or your fluid dynamics twice as fast, but then you lose 30% CPU performance, that doesn't matter because you still have an overall gain. But that may not be the case in multimedia. One interesting point that I don't think is really talked about that much is these kind of systems are available on AWS, and if you run said instructions on a particular CPU, you would actually throttle everybody on that die, which is quite an interesting phenomenon. Starting to be phased out, thankfully, but it is certainly an interesting point with regards to actually the cloud being a shared resource. It is genuinely a shared resource. But it is physical hardware underneath. There was some use in the sense that you could use new instructions, but with the older, smaller registers, and I'll talk about that a bit later. It can still be beneficial. And more recently, all of this basically, I guess, stems back to the fact that Intel have really struggled to compete in the last couple of years. I think they were stuck on 14 nanometers, now on 10 nanometers. It's the key reason their share price has gone through the floor. They've really struggled to move to the next sort of generation of, not architectures, but next generations of sort of silicon. And so only very recently the new Ice Lake 10th and 11th generation Intels were the first to have no throttling. So this was actually usable only, I think, in the last year or two. This has got more complicated. Intel made a giant mess of things by removing AVX-512 support in the consumer processors from their 12th generation. But on the other hand, AMD have put them in Zen 4, but then only half implemented AVX-512. But on the server side, you can still have access to them. So on the cloud, I believe most clouds ship the sort of server-grade CPUs, so you don't really see this problem. So if this is something you want to play with, this is the easiest way is to buy an 11th gen Intel NUC. You can buy them very cheaply, like a couple of £100, and get going. This is what I have in our lab for the FFmpeg project, for example, so anyone can log in and start developing. So let's look at existing work in multimedia using AVX-512. Most importantly, I think, the David project. So David is an AV1 decoder. It's a recursive acronym. They've had AVX-512 support for quite a while. Astonishing project. It has 200,000 lines of handwritten assembly. I don't think there's anything like it, at least publicly known. I'm sure there are things in private, but certainly things out there. Truly astonishing project. And AV1 decoding is really helped by AVX-512 because it has very large block sizes. So it has a 10 to 20% faster overall decoding. So I forgot to mention, I guess the key thing about these large register sizes is they're very sort of amenable to things like multimedia, because as we move from HD, say, to 4K, you have these larger and larger pictures, and you want to, say, process pixels all at the same time. So you want to do multiplies or additions, and you're really helped by these larger sizes. So if you go on the internet, you will find a lot of people who are wrong and will continue to be wrong and have been wrong for the last 10 years. And they still to this day believe they are right, but they are wrong. So the approach we use is a very classic old school approach that projects have been used, such as FFmpeg and X264 to assembly language, where we don't use these things called intrinsics, which are kind of helpers, I guess. They kind of try and abstract this away into sort of more normal code, but at the loss of control. This is what a lot of people on the internet think is good enough, but they are wrong. Nor inline assembly, which is kind of quite outdated now. People don't really use that anymore. It's about 20 years old. If you look at code about 20 years old, that was a kind of fashion. Some exceptions, I think Linux uses inline assembly because it has special needs as an operating system, but this is generally not used anymore. People on the internet think intrinsics or inline assembly is good enough. They are wrong. So the way to do that is really, and I'll show this in a minute, is to detect CPU capabilities when your application starts, because you don't know, for example, where your application will be running. It could be running on a phone, or well, maybe not an Intel phone these days, but something very low powered to something super powered. And you have to go and figure out at runtime what's available, because you may not know. And unfortunately, as I mentioned, because of AMD, because of Intel, it's maybe even worse than a Venn diagram these days. It's more of a pivot table. But in practice, we've boiled this down to two things that we care about. So in FFmpeg, you call this function get CPU flags, and it goes and figures out what your CPU is capable of if it can do AVX-512. So this is kind of the old school one with the throttling. And this is kind of the new one. So ICL stands for Ice Lake. And you can see there are all these different combinations of functions of new types of functions that are available. Each one of those is an individual test. So in principle, the Venn diagram could include every single one of those in some combination. But in practice, so far, before someone comes along and makes an even bigger mess, it's these two that we care about. So a real-world CPU will support either some of the older ones, AVX-512, and then on top of that, AVX-512 iSync. Just to sort of introduce a few concepts before we go forward. One of the biggest challenges in older AVX code, so this was non-512, so the older 256 variation, is you have the registers are actually split into these things called lanes. So actually, whilst you do on paper have a 256-bit register in the old world, in practice you work on these two split lanes, and you operate in those lanes, and you can't actually move, without a lot of pain, move between the lanes. This is a big limitation in all the AVX2 code. If you need to move data from this lane to this lane, there's quite a big performance penalty. Okay. So I talked about op masks, also known as K masks. These are kind of new. It's kind of interesting what you can do with those. New set of registers entirely, completely new. There's no historical precedent. And you can set them such that each element, and I'll show some examples in a second, that allow the destination register to remain, say, unchanged or set to 0. So, for example, add is probably the easiest one to kind of think about. You have various elements. So in this case, it's a word, so it's a 16-bit element. So I'm not going to try and work out the maths on my head. I think 32 elements of 16-bit in a ZMM, if I'm right. So you want to add, add these two together, and then output that in ZM1. So what the K-mask lets you do is set some of those values to 0. You might want to do that for some reason, or remain unchanged. Add is kind of a trivial case because you can obviously add 0 and the value remains unchanged. So it lets you manipulate each output on an individual basis if you need to, say, mask it out in such a way. And there are special instructions to manipulate those K-masks as well, which makes life really confusing. One thing to point out, because of this 30-odd-year-old history, the Intel instruction space is one of the most complicated and confusing out there. And I think I'll show some, at least relate to the Intel manual, which I think it's thousands of pages long at this point, literally covering some of these historical cases from the 1970s that some odd bit of the US military might still use, and probably is so mission critical that it still has to be kept there. Famously, I think in the early 2000s, Intel tried to scrap all of this and had massive pushback with the Itanium. So it's one of the massive and sort of most remarkable pieces of technological history that we still use every single day. Clicker's not working. So by far the most important set of instructions in multimedia are shuffles, also known as permutes. So this is a good example of a shuffle. So you have these values in a register, and you may want to shuffle them around. So let's say put E in the position that A was, move A around, maybe 0 some of them out. C maybe you want to put in this position, duplicate them, for example, and just move them all around in any sort of combination. By far the most important instruction in multimedia. And AVX-512 gives you this new instruction called FFmpeg. And historically, there was an older instruction called PShuffB, but this sort of restricted you to a single lane. But now you have this new instruction called FFmpeg, which lets you cross lanes. And I cannot really stress, I was talking to some of the best assembly programmers, this is a revelation. I cannot stress that in their lives. The amount of stress to try and get past these lanes and complexity that's now not needed is quite remarkable. PShuffB let you 0 a value out. You can't do that anymore. You have to use K-masks. Probably the most obvious use for this is a zigzag scan. So this, in the famous FFmpeg logo, is the zigzag scan. So you can load a bunch of data and then rearrange it in a zigzag. This basically there to sort of move larger coefficients to the beginning so you can compress them better. So you can do that now in a single instruction, kind of remarkable. It was a giant mess before. Also, you can do much more complicated things in AVX-512, such as permute from 2 registers. So this one is from a single register, but you could imagine there was a second register with IJK, LMN, and you can now selectively go and choose which this one I can take from this one, or make it 0, and do duplicates. So very, very powerful. Variable shifts. This wasn't something that was easily doable in the past. So if you want to have a bunch of data and you want to shift each element by a different number, there were lots of tricks, especially on right. Left is kind of okay because you can do a multiply. So a shift is by definition a multiply. A left shift anyway is by definition, at least a logical left shift is by definition a multiply by a power of 2. This is really confusing. It's a letter soup. I can tell you the first version of this presentation had the word shift spelt in a very unfortunate way. And thankfully one of my colleagues pointed this out. So yes, you had to use lots of real tricks, especially for right shifts. If you want to shift a bunch of different values by a different value right, you had to do lots of tricks, and there were limitations to these tricks. For example, you couldn't say do a right shift by 0, so you had to separate out all the values you wanted to right shift by 0, ignore them, put them back in afterwards, do your shifts. Left shifts as well, still kind of useful. You could do a multiply, but the variable left shift instructions are kind of faster than multiplies. But yeah, word soup, super confusing to read. One of the challenges, I think, is the word soup of it all. VP turn log D is a remarkable instruction. I don't think there's been anything like it. Really the kitchen sink. So you can program a truth table. So if you go back to, if anyone remembers your sort of GCSE science, where you had these kind of, you drew these little diagrams of the lot of your ones and your zeros, and you have an and or your or XOR. You can actually do, in theory, up to 8 different truth tables in one. So you basically program a truth table into the instruction, so using this value here. And then you can say, oh, I want, for example, this example is quite interesting because you can do the equivalent of a ternary operator on each bit, which is kind of remarkable. It's been possible, but with a lot longer instruction set. You can do, if that bit is set, choose, pick the bit from this register, otherwise pick the bit from this register for every single bit. And this, you could do a whole presentation on this entire instruction itself, and this guy has. All sorts of interesting things you can do, and I'll try and give an example afterwards. What else is there? Oops, gone too far. No, it's frozen. Nope. So let's look at a real-world example. This is real code that we use in our company. So. V210. So various data formats need to be packed if they need to be transported over a network or a PCI bus, for example. This is a good example of one of them. All sorts of different flavors of this, but this is kind of one of the most common ones. So it takes 3 8-bit data words, extends to 10 bits, and packs them into 32 bits. So 3 sets of 10 is 30, so that just about fits in 32. So you have a load of the Y plane, which is the Luma plane. So that's your black and white plane. Into the YMM register, so the lower part of the ZMM register, and then you have these inserts of your 2 color planes, so your U and your V, into the sort of lower upper, and then the upper part, for want of a better phrase. And the bit that's remarkable is you can just do this giant permute, which was a complete nightmare, and it was a lot more instructions. It took a lot more CPU before to just permute them all into one giant sort of list. This was remarkable. It was never possible to do that. You really spent a lot of time trying to handle this cross-lane situation. The clip is kind of there are some values which are illegal for various historical reasons in uncompressed video. Multiply add basically is a trick to kind of separate some of these values. So it's this pmad, I think it's p multiply and add these elements together. This it's difficult to explain without a diagram and in length, but the fact you can do all of these in one go is kind of remarkable. You can do the center element. So this element here needs a left shift. And then we can do VP turn log D, which is kind of remarkable. So we can do a mask and say, particular bits I want from this one, from M0, and particular bits I want from M1, and mask those out manually in one instruction. And that's basically it. And this used to take a lot more And I'll show you some benchmarks in a minute of that. So we can look at some benchmarks on real CPUs. These are not obviously scientific, because if they were scientific, you would run them multiple times, have a plus or minus, have an average and a standard deviation, etc., etc. But these are just ones I picked to kind of show. So on the older systems, the ones that even have the CPU throttling, you still get some benefits. It's not big, but it's enough that it's worth it. So this is basically as a result of VP10logD, so this sort of magic kitchen sink instruction. But you still have the cross-lane issues, etc. So this is the older stuff. So we can still improve all the CPUs in the field, which is really nice. But where you really have your big wins is on the Ice Lake with your cross-lanes. So this is the ICL. So yeah, as I mentioned, people on the internet are wrong. Oh man, they are wrong. You can never beat the compiler. It's said pretty much every day on Twitter and Hacker News. They are wrong. Like, there you go. You can beat the compiler by a factor of 20 easily. And this has a big impact in the real world, because imagine this code, for example, wasn't fast enough for real time. You'd have to say it ran, I don't know, 1.5 times too slow. Then you have to do all sorts of complicated stuff with threads, trying to split them across cores to do that. But now that you've made it 20 times faster, it's essentially negligible. So you can move on with your life, and all that complexity is now gone. So it has a sort of second order effect, actually. Though even then, if you look at it, the old one is 10 times faster, so it's kind of decent enough as it is. Even if it needs 150% of a CPU core, so it runs too slowly, you've made it 10 times faster. Now that takes 15% of a CPU core. If you do that in terms of gear, that's from 10 servers to 1 server, and then now with Ice Lake, that's 20 servers you once had. Now it's gone to 1. It's kind of remarkable. So what's next? We really hit the. Just to be clear, this is the simplest of the simplest in V210. But anything that's really doing processing across a line or a frame, so anything that's doing video filtering, scaling, anything that's doing comparisons. Haven't really talked about comparisons, but comparisons are really interesting because there's lots of use cases for this, not just in multimedia. VP10logD, lots of places where they're doing variable three-way booleans, so you can use VP10logD. Variable shift is very commonly used. You need to shift data via different variable amounts. You can move those very easily. We actually did that at work. What to look at? The Intel manual is very, very verbose. Like I said, it has 30 plus years of history defined, but it is very, very clear cut, and it defines things very, very clearly without ambiguity. But otherwise, there are things like this Office Daytime website, which is really good. It goes and maybe you should have put a screenshot actually, but it shows all the instructions in kind of a table, so you can see how they sort of are similar but slightly different. So it's very useful to understand it. I found it very useful personally. So yeah, Q&A. I think that's it. Yeah. On the mic.